Hello.
Tonight we're going to have a talk by Theo O'Neill. She had got her BS from the University of Virginia in astronomy and physics, and she's now working on her PhD in astronomy and astrophysics at Harvard University. She's going to talk to us about bubbles in the Milky Way.
Hey, hey.
Tiny bubbles.
Great. Thanks, everyone. Can you hear me all right?
Yes, we can.
Perfect. Let me just get my Zoom screen all set up, and then we'll be ready to get started. Oops, I did not want to go there. And then let's just find my cursor somewhere. Huh, that's interesting. Okay, perfect. And then let me try and get rid of the recording meeting button.
We can't see that.
Okay, perfect. I'll just leave it up there then. So yeah, hello everyone. As you just said, I'm Theo O'Neill. I'm a PhD student at Harvard University. I primarily work on the structure of our own galaxy, the Milky Way, and I'm particularly interested in how young stars reshape the environment around our own sun, which we call the solar neighborhood. And so tonight I'll be giving a overview of the research that I'm doing, focusing on how stars feed energy back into our own Milky Way to create structures that we call bubbles. And so I thought it would be useful to start with a high-level overview of how stars actually form. And the video that I'm showing here is from a suite of simulations called StarForge. What you're seeing here is an overview of what we call the interstellar medium, or the space between stars. This is a part of everything in between the stars is full of dust and gas. This is shown here by these pink and purple clouds. When these clouds get dense enough under the force of gravity, they can collapse and form young stars, like we're seeing here in this video. These young stars quickly evolve and start to reshape their environments. They create huge jets shooting out of these stars, there's stellar winds, and eventually massive stars might explode as supernovae. They start to clear out the gas and dust in their environments, like we're seeing now in this phase of the simulation, and lead to an evolved star cluster surrounded by this kind of fragmented, clumpy interstellar gas and dust. So most of my work focuses on the process of what happens once stars form in the interstellar medium, and then how they go on to continue to affect their environments on the scale of galaxies. Stars not only form in the interstellar medium, but they also die in the interstellar medium. By death, what I mean is for massive stars, the formation of supernovae, which I think most of us might be familiar with. So when very massive stars, so generally 8 times or more the mass of our sun, become very evolved, they can explode as supernovae and feed an enormous amount of energy into the interstellar medium as basically an expanding shock wave. What I'm showing on screen here is 2 examples of very famous and I think beautiful supernova remnants, imaged on the left with the Hubble Space Telescope and on the right with the James Webb Space Telescope. Because stars tend to form in clusters, like in the simulation that I showed on the previous slide, supernovae also tend to occur in clusters. And so if you have multiple supernovae go off in a short amount of time in the same space, the effects on their environment in the galaxy can really be quite astonishing. I have a cartoon video here, not quite as beautiful as a simulation, but I think gets the point across quite well. So if we have our molecular cloud, so this is a cloud of atoms and molecules, gas and dust, shown here in blue, that starts to fragment and form quite dense clumps of gas to form young stars. These young stars might then start to evolve and die and explode as supernovae, which creates the an expanding shock wave, which we call a bubble, that sweeps material like gas and dust out of its environment and leaves behind a low-density void. As this bubble expands under the power of additional supernovae, clouds on its surface might start to reform as even denser than they were before, and lead to the formation of a whole new generation of stars to start the process over again of creating more supernovae and carving out more voids or bubbles in the interstellar medium. And so this is a prediction that has been longstanding in astronomical literature. This dates back over 50 years now. Some of the first papers about this were in the 70s. So I'm showing one of them here with a schematic cartoon view of what this sort of bubble-driven interstellar medium might look like. This idea has held up remarkably well over the last 50 years. So starting from theory, I'm showing now here some recent simulations of full galaxies. You can see these galaxies are rotating. The pink stuff here is the gas and dust in between the stars, and you can see the creation and then rotation of these large bubbles in this galaxy. When we compare simulations like the simulations that I'm showing here to observations of our real universe, they tend to agree remarkably well. I'm showing here, I think, just a fantastic image taken by the James Webb Space Telescope of the nearby galaxy NGC 628, which is just riddled with bubbles and voids in the space between the spiral arms of this galaxy. When I first saw this image, I think 2 years ago now when it was released, I was just blown away by how much substructure and how many bubbles really exist in the interstellar medium. And so the heart of what I'll be talking about today is how we can connect bubbles in other galaxies, like the one that I'm showing here, to theoretical predictions for how bubbles behave coming from simulations, to the actual 3D structure of bubbles surrounding our own sun in the region that we call the solar neighborhood. And so the video that I'm showing here is what I'll also end the talk with. So this is kind of me spoiling the talk at the start. But so the heart of this presentation will focus on bubbles across all scales and regimes in our own galaxy. So as a starting point, I thought it would be useful to consider the history of our own sun and our own solar system's interactions with bubbles across the last tens of millions of years. Bubbles in the interstellar medium are so common that we actually, as I just said, happen to live inside of one, which very creatively is named the local bubble. I'm showing here an artist's rendition of what this local bubble looks like with the sun in the center of this bubble, very much not to scale. My collaborator and advisor, Catherine Zucker, who is a scientist at the Smithsonian Institute associated with Harvard here in Cambridge, Massachusetts, put out a paper about 2 years ago now, summarizing some new discoveries that we've made about the effects of the local bubble on its environment, which I'll summarize now. So the local bubble is about 1,000 light years wide in diameter. And what Catherine found is that its expansion into the interstellar medium under the power of clustered supernovae is really responsible for the birth of nearly all young stars in our solar neighborhood. This includes well-known star-forming regions, which some astrophotographers in the room might be familiar with, so places like Taurus or Lupus or Corona Australis, really well-known nearby star-forming regions that we've known about for many, many years. What Catherine did is used new data on the structure of the interstellar medium and on the motion of young stars to reconstruct the evolutionary history of our solar neighborhood. And what she found is that about 14 million years ago, a cluster of about a dozen supernovae started to occur, which then, yes, this is a very dramatic cartoon, but started to carve out this shock wave, this bubble in our local interstellar medium. As this bubble expanded, it swept up the gas and dust in our early solar neighborhood and led to the formation of those new star-forming regions on its surface. I just showed a cartoon, but we have real data to back this up as well. The cartoon is now on the left, and on the right, I'm showing the inferred paths of young stellar clusters in our solar neighborhood over the last 14 million years. So we have this expanding bubble leading to the creation of new molecular clouds and new generations of stars. And as I said, many of these new star-forming regions are quite well known and are responsible for some of what I think are the most beautiful astronomical images of the nearby universe. I'm showing here an image in the top right of the Ophiuchus Nebula, which is located on the surface of the local bubble. And then on the bottom left is a very, very high resolution view of a protoplanetary disk, so a system forming new planets around a young star in the Taurus molecular cloud. So the local bubble really does seem to have reshaped our environment in quite a dramatic way. And a question that I often get is, why is the sun in the center of this bubble? Isn't that a little odd? Isn't that a little unusual? And so what Catherine found is that our sun was actually about 1,000 light years away when this bubble started forming. So as we reconstruct our own sun's motion through the Milky Way over this time period, we find the sun probably entered the local bubble about 5 million years ago, passed through that swept up shell of dust and gas, and now in the present day, just by luck, happens to sit near the local bubble's center. So it's really a remarkable accident of timing that in the present day, we happen to have this privileged position, this privileged view of the interior of a bubble. So we've known about the local bubble for over 50 years now, and Catherine's work is just the latest in a series of discoveries about this structure. But what makes this recent discovery possible is the development of space telescopes, which can tell us the precise distances to stars in the interstellar medium. And this really resolves a long-standing issue in astronomy, is we can look out into the night sky, like in the view I'm showing on the right of the screen here, and we can see all sorts of stars and other galaxies, but accurately measuring how far away a given structure is actually quite difficult. And so the Gaia Space Telescope, which was launched a little under a decade ago now, has really transformed our abilities to measure distances to stars. So this image that I'm showing here on the right is actually, it's not a photograph or an image at all. This is a map of the number of stars that the Gaia Space Telescope has been able to observe at every point over our night sky. And so what we see is that this is really, we can see that there's more stars in the center of this image, of this map. That's the disk of our galaxy, where the majority of the stars in our galaxy are concentrated. But we can additionally see a variety of black filamentary structures blocking our view of more distant stars. And so what those structures are clouds of nearby interstellar dust. This is a collection of molecules of all types, which tend to be from less than a micron to a few microns in size. I'm showing a few example images taken here on Earth, of course, not in space, of what these dust particles might look like. So when starlight is being blocked by dust, and we have the distances to stars in our sample, we can then start to do exciting reconstructions of what the 3D structure of dust in our own Milky Way actually looks like in a way that we couldn't before. And so I'll show this cartoon example of how this process works, of what we call 3D dust mapping, so finding the distances to dust clouds. So when we look out with our telescopes into the night sky, we might observe some sort of star. That light travels to us and we take an image of the star. There's a variety of information that we can derive about the properties of stars that we image, such as their colors. So as we may or may not know, stars come in a variety of different colors. You can see this just by looking up at the night sky. Some are redder, some are bluer. But what happens when a star passes through a cloud of this interstellar dust, the light that travels to us ends up looking much redder than it would have if the starlight hadn't actually traveled through a dust cloud. You can see this clearly when looking out into space. I'm showing here on the right an image of a very dense, very small cloud of dust. In the center of this image, where it's totally black and it looks like there's no stars, that's just where the dust is densest and blocking almost all of the background starlight from getting through. And you can see on the edges of this dust cloud, the stars tend to look redder than the stars that are not blocked by the dust cloud at all. So when we have millions to billions of stars, like we have now been made possible with the Gaia Space Telescope, we can use high-level statistical and computational techniques to infer how far away the dust clouds are from our own sun based on the dust's effects on stellar colors. And so, since with the Gaia Space Telescope, we now have distances to millions and billions of stars, and and high quality measures of how much stars' colors have changed from their original types, we can create 3D maps of dust in our own solar neighborhood. So I'm showing here on the left is an example of what the output of this reconstruction process might look like. This is a map of the dust near our own sun, shown on the left here, with about 80 light year resolution, which is quite good. And this is the map that was used to make the very smoothed model of the local bubble, which my collaborator Catherine used for her analysis of the history of star formation on the surface of the local bubble. But what's really exciting about being working on the interstellar medium right now in 2024 is that we're getting new data from all sorts of telescopes every day, including the Gaia Space Telescope. And so in just the 5 years since this dust map on the left was released, new data and improved techniques in our reconstruction methods have allowed us to generate 3D maps of dust in the solar neighborhood at 25 times higher resolution than was possible even 5 years ago. So I'm comparing here on the right now is what's currently my favorite 3D dust map created by a collaborator of mine. And so you can see that the large scale structure of these two maps around our sun, which is shown by the yellow dot in the center, is broadly the same, but there's a lot of increased resolution and small scale details in these maps. And so what this allows us to do is understand the structure of our solar neighborhood at much higher resolution. So earlier this year, when this map came out, myself and my collaborators decided to create a new model of our local bubble using this higher resolution 3D dust map. And so the results of that modeling are shown here. I'm showing here is a link to an interactive figure from the paper that we've created with this new model of local bubble. You can scan the QR code if you'd like to play around with this figure yourself. But so what I'm showing here in shades of purples and yellows is the 3D dust. And then in blue is our new model of the local bubble, as well in other colors, a variety of other structures in our solar neighborhood. I'll show here is just the new local bubble model by itself. This is colored according to the density of dust on the surface. But so the punchline here is that the local bubble is not this smoothed, continuous surface like earlier models might have suggested. It's highly fragmented. It's really irregular in shape. There's all sorts of weird extensions coming off of it. And then to me, maybe the most exciting new feature of this model is that it appears really asymmetric from the top to the bottom, or what we would call the north in the top and the south in the bottom. You can see here that the northern half of the local bubble appears markedly different than the southern half. It's much more extended. And generally, it appears much less spherical, much less bubbly in shape. And so what we think that this new modeling actually indicates is, again, the validation of of original theories about the behaviors of superbubbles in galaxies. And general predictions that as these bubbles expand into the disks of their galaxies, which is shown here on the left by the shaded in region, they can eventually start to burst out of the disk of their galaxies. This original cartoon is great, but I'm going to replace it now with a more up-to-date version from a more recent paper. So the general story here is that as these bubbles expand under clustered supernovae, they eventually start to reach the height of gas in the full disk of a galaxy like our own galaxy, the Milky Way. If the right physical conditions are met, these bubbles can actually continue to expand past this height of gas in the disk of a galaxy. And if this process occurs, we call that the bubble has broken out of the disk of a galaxy. You can also call this forming a chimney out of the galaxy, where chimney refers to the enhanced elements from supernovae being thrown out of the interstellar medium in the same way that smoke from a fire at the base of a chimney can then be thrown out of your house. It's a bit of a tortured metaphor, but there we are. But so this idea of superbubble breakout is an old one that's again validated by both theory and in simulations. I'm showing here on the left a recent simulation of a bubble forming and then breaking out of the disk of its simulated galaxy. You can see a really quite quite violent explosion here over tens of millions of years. And so what we found here is that the local bubble is caught in the act of this sort of breakout of our own galaxy's interstellar medium. This is also reminiscent of when we look at external galaxies, like I'm showing here, the M82 galaxy, where we see powerful outflows being driven out of galaxies on scales much larger than the local bubble themselves. So what we think we found with the local bubble is a local analog to these powerful outflows and galactic winds being launched from other galaxies. So that's just one exciting application of what can be found from 3D disk mapping and from studying the local bubble. There's a lot of other cool science that can be done with this as well, but one that's near and dear to my heart is the question of how magnetic fields in galaxies interact with this whole picture. And magnetic fields are kind of the boogeyman of astronomy, but I think they're very important to consider when we're thinking about the picture of how gas and dust in galaxies can interact and evolve over meaningful amounts of times. So when we look at other galaxies, we tend to see very strong and powerful magnetic fields throughout their interstellar media. I'm showing here on the left a spiral galaxy M51, imaged by the Hubble Space Telescope. And the drapery kind of convoluted pattern overlaid on top of it is showing the orientation of magnetic fields in this galaxy. And what you might notice is that the magnetic field orientation tends to follow these spiral arms in this galaxy. We also live in a spiral galaxy, our Milky Way, but because we're inside of it, it's quite difficult to actually observe this sort of behavior directly ourselves. But so we're faced with this prediction from theory and this observation from external galaxies that magnetic fields tend to align with galactic spiral structure. But the challenge becomes that in our own Milky Way, since we're inside of it, it's really quite difficult to observe magnetic fields in 3D. So when we're looking at our own Milky Way, we're forced to instead look at the kind of projection of magnetic fields in our galaxy onto the plane of our sky. What I'm showing on the right of this screen is a map of magnetic fields in our own galaxy taken by the Planck satellite. The colors are showing the intensity of dust integrated along the line of sight from our own sun out to the edge of our galaxy. And the drapery patterns are again showing the orientation of magnetic fields. So we're faced with a situation where we have magnetic fields in galaxies, we have spiral arms, we have bubbles, and we're trying to sort out how exactly these structures are interacting with each other. And so because we're inside of the local bubble, we occupy this position where every direction we look, we not only see the rest of our galaxy, we also see the same local bubble along all lines of sight. And so what we're able to do is combine a series of basically assumptions about how our 2D sky relates to our 3D local bubble and where our observed 2D magnetic fields or polarization measurements, for those more technically minded, are actually originating in 3D space. I won't talk a ton tonight about the specifics of how we do this sort of transformation to map magnetic fields in 3D, but if anyone's interested, please feel free to ask me. I'd love to talk more about it. But so the net result of this sort of analysis is the creation of a reasonable 3D model of what our local bubble's magnetic field likely looks like. And that's what's being shown in this video here, overlaid in an artist's rendition of what our Milky Way looks like. So the vectors, the lines on the surface of this local bubble, are showing our 3D magnetic field orientation, and the colors are showing the distance from the sun to the surface of the local bubble. So this is quite interesting, but at its heart, it's a visualization challenge to show data like this, but we can then go further and try and reconstruct what the initial orientation of the magnetic field in our local portion of our Milky Way would have looked like before the local bubble started expanding into it. And again, this is a result of the expected physical behavior of magnetic fields in the interstellar medium. So if we perform this modeling, we can come up with an informed model of what the initial orientation of the magnetic field in our solar neighborhood would have looked like. I'm showing this by itself here on the left, before the expansion of the local bubble. And on the right, I'm showing what this would look like in the present day. So this is showing a top-down view of our local bubble from looking from outside of our galaxy. The vectors on the local bubble surface are the same as in that nice video that I just showed, and the blue lines are showing our inferred magnetic field orientation. And what's really, I think, notable about this analysis is that we find an initial orientation that is parallel to the local portion of the spiral arm in our galaxy. So the red line that's running through this figure on the right is one part of our local spiral arm, which is shown in left, overlaid on an artist's rendition of our Milky Way. And we find a magnetic field orientation that is aligned with this spiral structure. So again, this is this sort of happy agreement between observations and modeling of our real universe with theoretical predictions for how the interstellar medium should operate and with our observations of external galaxies. That's all that I'll say about magnetic fields right now. But then the final kind of heart of the analysis that I'm working on as part of my PhD is the question of how unusual is the local bubble in its size and its properties, stuff like that. And I think the best way to really answer that is to build up a sample of other bubbles in our own Milky Way so we can really get a sense of the sort of population that we're dealing with here. So I'm showing here is that new 3D dust map created from using the Gaia Space Telescope in white, with my new model of the local bubble shown in blue and the sun in the center in yellow. And so it's quite easy to look at this map by eye and say, hey, okay, I think maybe over there, there's a spot that could be a bubble, or maybe over there, there's something. But it's difficult to create any sort of meaningful scientific conclusions from that sort of by eye analysis. So what we really need is informed, like, statistical methods to be able to characterize what is likely to be a bubble in this space. And that's the heart of what I've been working on in the last year or so. I won't explain the method tonight, but the net result of this analysis is shown here. This is the video that I started my talk with. So we have the sun in yellow in the center of this video, the local bubble is in white, and then in shades of blues and purples are a variety of other candidate supernova-driven bubbles throughout our local interstellar medium. This volume spans 8,000 light years on a side, and we're able to identify hundreds of other bubbles of all shapes and sizes in the space near our own sun. And we're able to map their structures in 3D for the very first time. This is exciting, not just from the perspective of building up a statistical sample of bubbles, but it also allows us to try and pin down how unusual the local bubble is within this population. And so just a few examples of these sort of metrics. The plot that I'm showing here is the overall distribution of sizes of bubbles that we've identified. So the radius of a bubble in this space is shown on the x-axis, and this is basically like a histogram. And then the vertical purple line here is showing what the radius of our own local bubble is in this parameter space. So we can see our own local bubble is slightly larger than the average bubble, but it's still well within the norms of this population. And there's a variety of other physically motivated correlations and properties of bubbles that we can check. I won't really get into this now, but the main point is that our local bubble, which is shown here by the purple points, by all accounts appears exceedingly average in the population of bubbles in the solar neighborhood, which to me is very reassuring. I think us being average is a great thing. Because, you know, go back to the Copernican principle, we don't really want to be in any sort of special or privileged position in our universe. So existing within an average bubble is a-okay by me. Most of the analysis that I've been talking about and the analysis that I showed on the previous slides has been focusing on the 3D universe. But there's a lot of exciting things that we can do with two-dimensional views of our night sky as well. What I'm showing here is an all-sky map of hydrogen alpha, H alpha, throughout our Milky Way. I hope that H alpha might be familiar to any astrophotographers in the crowd. This is an atomic transition of hydrogen, and it's really remarkably well correlated with young stars and with recent energetic injections of young stars into their environments. Just for one landmark here on this night sky, in the center, you'll see the Orion constellation. I'm overlaying here and comparing hydrogen alpha to the optical view of our night sky. So you can see in red, hydrogen alpha, very complex filamentary, and then in black, you can see the well-known Orion constellation. When we project the 3D bubbles that we've found in our 3D dust maps back to this 2D night sky view, we're able to reconstruct a variety of very well-known features, including a large superbubble in the Orion constellation called the Orion Eridanus superbubble, a well-known feature called the Gum Nebula, as well as a whole variety of other structures, many of which appear correlated with this H alpha, this tracer of recent star feedback. So this is encouraging in that the methods that we're using really are probing this question of how stars feed energy back into their environments and create bubbles. So finally, another big question that I'm interested in is how unusual is our solar neighborhood as a whole? We're able to now probe a small fraction of our Milky Way galaxy, and we have this catalog of bubbles, but how actually are we surprised that there's this many bubbles, or are there too few? How can we ground these observations in the larger context? And for me, what I think is exciting is comparing our solar neighborhood to nearby galaxies, like this same image of NGC 628 that I showed at the start of this talk, which is really riddled with bubbles. So an ongoing part of my PhD is identifying analogs of the local bubble and other bubbles in this galaxy and in dozens of other galaxies as well, and comparing them to our own solar neighborhood. So I'm showing here just one potential analog of the local bubble in this galaxy NGC 628, compared at the same physical scale to our own local bubble from a top-down view. This is just one of dozens to even hundreds of potential analogs of our local bubble. We can additionally build up an even larger catalog of bubbles throughout this galaxy and many others. I'm showing here on the left the full James Webb Space Telescope observed image of this galaxy, and overlaid by the ellipses and circles are candidate bubbles created by supernovae and other dynamical processes in this galaxy. And on the right, I'm showing that same map of our own solar neighborhood with our collection of candidate bubbles. So I think this is a really exciting time to be working on bubbles, both in other galaxies and in our own. One thing I do want to highlight is that we're still only probing a pretty small physical scale in terms of what we can map with 3D dust in our own solar neighborhood. If we were to overlay our solar neighborhood on this other galaxy at the same physical scale, it would occupy a pretty small portion of this galaxy by area. So one exciting innovation that I'm looking forward to seeing in the next 5 to 10 years is how much further into our own Milky Way galaxy we can extend this technique of mapping our own interstellar medium in 3D. So stay tuned for more on that. So I thought I would summarize now with a few takeaways from this tour of bubbles in our own Milky Way. We live in a bubble called the local bubble, and we found that almost every nearby young star lies on its surface. This provides strong evidence for decades-old theoretical predictions that bubbles can sweep up gas and dust and create new clouds that can form new generations of young stars. We found that our own local bubble appears to have burst out of the disk of our Milky Way galaxy and formed a chimney into the exterior vertical portions of our galaxy. We've analyzed the structure of magnetic fields on the local bubble and found strong evidence that the magnetic fields tend to be aligned with galactic spiral structure, which again is in agreement with predictions from theory and simulations. And then finally, we find that the bubbles appear to be basically ubiquitous throughout the solar neighborhood and in nearby galaxies, which strongly implies a bubbly Milky Way and a bubble-driven evolution for the interstellar medium across millions to billions of years in timescales. So with that, I would be very happy to take any questions. I left lots of time, I think, for questions. So if there's any aspect of what I said that you'd like to hear more about, I'd be very happy to elaborate. And thank you so much for having me. Really appreciate it.
Well, thank you.
Thank you, thank you.
All right, what I'd like to do is take some questions from the room first, then we'll get to the Zoomers, and I'm going to sneak in my traditional first question. It's about magnetic fields and those spiral arms. Is there a causal relationship going in one direction or the other? Is there an influence going in one direction or another? It's not coincidence. So are magnetic fields guiding the spiral arms? Are the spiral arms creating magnetic fields? What's the scoop?
That is a fantastic question. And I do not actually have an answer because no one has an answer. This is one of the most hotly contested questions in the field of how magnetic fields affect galaxy evolution. So you're absolutely right. I also don't think it's a coincidence that magnetic fields appear to trace spiral arms. But the question of whether the magnetic fields were initially oriented in some spiral and that encouraged the gas and dust to follow that into spiral arms versus if the winding and rotation of spiral arms kind of dragged the magnetic fields along with them and left over this residual spiral pattern. It's very hotly contested. I know people who have staked entire careers on this question, and I'm not really sure I want to take a stand one way or the other, but that's a great question.
Okay, well, I struck out Mario. What do you want to ask?
Early on, you showed an animation of the bubbles being sheared and then gradually disappearing. And from the amount of time, I would estimate that would probably be 60 to 100 million years because it went like halfway around the galaxy. But there's plenty of bubbles. So the fact that they're not long-lived galaxy-wise, can you make an estimate by looking at the number of bubbles as to the supernova rate and both now and in the past?
Yes, yeah. Again, fantastic question. You absolutely can do that. It becomes tricky to distinguish what is one distinct bubble versus if two bubbles that were unrelated happen to merge via this rotational shearing processes. And there's an additional complication coming from the fact that not every void in a galaxy that looks like a bubble actually is a bubble. Sometimes there just doesn't happen to be stuff in a place, and then in the course of galactic rotation and shearing, it ends up looking basically indistinguishable from a feedback-driven bubble. So one could absolutely imagine placing some sort of upper limit on the supernova-driven rate in a given galaxy. I think for observational data, you could really only do that for a timescale of 10 to 50 million years. I agree with your estimate of 60 to 100 million years for bubble upper limits on a bubble life cycle. But in terms of separating out all these different confusing factors, I think you'd have the best luck in the very recent past.
Eleanor, yes.
Theo, you showed a slide showing the radii of the shells of bubbles that have been measured. But the images that we've seen make, especially our local bubble, look very porous. How defined are the shells?
It's a great question as well. So the shells are defined based on there being a continuous low density void in this 3D dust map. And then the shells are mapped. You map the dense dust surrounding this low density void. So the radius that I'm showing here is by calculating the equivalent radius that a sphere with the same volume as this shell would occupy in 3D space. So for structures like the local bubble, which have actually burst out of the galaxy, This is not the most physically meaningful metric, as if it was actually still encompassed in the disk of the galaxy. But you can see in this video here, for many of the small bubbles, they are roughly spherical and still closed because they have not, and maybe never will, reach that phase in their evolution of starting to elongate. If that provides any insight into that question.
Yeah, how does that affect the star forming region if it's not clearly defined? The new stars are formed on the outer, on the shell, on the outer.
Yeah, yeah. So that's a hot topic. I would say that for these large bubbles, where their shells appear to be more fragmented, they've had more time to sweep up more material and create denser clouds of dust and gas. And they also tend to be surrounded by other bubbles of all shapes and sizes. So you can imagine the compression between two bubbles leading to the formation of even denser clouds, which could then potentially enhance the local star formation rate. So a lot of our theoretical models for how bubbles evolve only consider an isolated bubble and don't really reflect this sort of scenario of clustered bubbles where you have star formation rates being affected by merging bubbles, interacting bubbles, forces like galactic shear. So the best that we can do right now is look at the properties of young stars on these bubble surfaces and try and then estimate what the past star formation rate would have been.
Thank you. Anybody else in the room? Bill?
Yes, what a great talk, Theo. Thank you. One question having to do with numbers, which I forgot, but you mentioned that the local bubble was driven by a number of supernova explosions. I can't remember the number, but whatever it is, I'd like to know how you and or your colleagues came to that number.
Absolutely. So the number that that my collaborator Catherine estimated was based on this older model of the local bubble. And what she did was look at the 3D velocities of young stars embedded on its surface to get a proxy for how fast the bubble is expanding in the present day, and then compared that with the present day size of this model of the local bubble to then infer, using statistical modeling, how much energy would have had to have been injected into the interstellar medium to carve out a bubble of this size moving at this speed. So you can imagine a kind of multi-dimensional parameter space that we have to explore in our models to create the number. And so I believe that the number of supernovae she estimated was somewhere in the range of 12 to 16 supernovae over the last 14 million years. But of course, that is model dependent. So we haven't done that sort of same analysis under this new model of the local bubble where we've had an outflow event. So I would imagine that number might change a bit. But I think that of order 10 to, maybe 24 supernovae would be reasonable based on this expansion velocity.
So basically, you're computing the kinetic energy of that shell.
Yeah, that's a good way of putting it.
And comparing that to the fiducial energy of a supernova blast of 10 to the 51 or 10 to the 52 ergs.
Yes, yeah, exactly.
Okay. And then, well, I'm going to get worse. And then you can always raise that number, because if it's a porous shell, a lot of the energy will leak out.
Yeah, exactly. So there's a lot of uncertainties based on the specifics of how your shell evolves.
But it's significant. I thought it was just one supernova.
Yeah, no, it's a few dozen. One supernova is maybe not even enough to carve out a full bubble. You could maybe clear out a space a few maybe tens of light years in size. But to get these sort of 1,000 light year wide bubbles, you do need that sort of clustered dozens of supernovae.
Thank you.
I have one more very little question. Is Bubble North aligned with Galactic North?
Yes, it is, in that bubble north is towards a galactic latitude of 90. If that is meaningful to anyone, I think it probably is. But so yeah, they're aligned.
I was wondering where I could point my telescope and be looking through less stuff.
Yes, yeah, that is a great question. So if you look at this plot here on the left side, this is an all-sky map in galactic coordinates of dust density. And so this region up here to the left is the lowest density dust. So if you convert from galactic coordinates to, RA and DEC or whatever coordinate system you'd like to have, this is where I would suggest looking for the least dust. And
Thank you.
that's incidentally useful for, things like cosmology as well, where we can get the most uninterrupted view of the very distant universe. So lots of fun things to do here.
Any other questions in the room?
I have a question.
Yes.
You said that it took about 5 million years for the sun to get to the middle of this local bubble, so I'm assuming it's another 5 million years to get to the other side?
Yes, yeah, of order of
We're gonna-
5 million years.
And we're gonna be going through, or the sun is gonna be going through presumably a star forming region at that other end, or at the other edge of the bubble. Is that going to be a problem? Is it more dangerous to go through that?
This is again, this is one of my favorite questions. So no, I don't think it's dangerous at all. But what is interesting is the effects of passing through a bubble shell on a solar system are not zero. So when we compare this time scale of the local bubble entering into this dense shell about 5 million years ago to the geological record on Earth, the rate of supernova created isotopes in the Earth's crust, we see peaks in the Earth's geological record at just about the same times that the sun would have passed into this local bubble shell, which is pretty cool independent evidence for this sort of transit. But then additionally, our own solar system is protected by a magnetic heliosphere from external radiation and high energy particles, things like that. And so because our local bubble has a magnetized shell, when the heliosphere passes through this magnetized shell, it might shrink, it might contract in response to this passage through another magnetized body. And so one of our collaborators, Merav Ofer, recently had a paper out examining this exact question of whether the solar system's heliosphere would have shrank and the Earth might have been exposed to interstellar space during this last transit. And the answer is maybe, with probably yes. So yes, in 5 million years, we might have a slightly higher incidence of high energy particles as a result of traveling through this magnetized shell, which I think is kind of crazy and pretty awesome.
Ask a quick,
Questions online?
one quick thing before Theo moves on from this. You bleeped for a second in my bandwidth when you said something peaked around 5 million years, which would have coincided with the sun entering the bubble. What was it that peaked that gives us evidence?
Yes, so it was an isotope of iron. So just a supernova created iron isotope in the Earth's crust.
Second, can you show that QR code? There was a simulation. You had a QR
yes,
code.
yeah.
Just starting to hit it. Brilliant talk, absolutely. And I really love the animation and the visuals. They're very helpful, very artistic, very creative. Thank you.
Thank you. Yeah, and there's that QR code. This paper was recently published just maybe 2 weeks ago now. So this is basically hot off the presses, and there's a whole website of 3D figures of the local bubble that you can play with on your phone or computer.
Thank you. Got it.
Anybody else online? I'll take that as a no.
We're good.
All right, Theo, thank you.
All right. Thank you, everyone.
Thank you
Thank
so
you.
much. This was wonderful. I really appreciate it.
Thank you. It's hard to follow y'all's questions in the room.
All right, thank you, Theo.
Bye.
Thank you, Michael.
Have a
Have
great
a
night.
great weekend.
Thank you.
Okay, before people start picking up their chairs, we've got a couple of things here. We have two telescopes that don't look like any telescope I ever imagined. You want to make sure you check out the one in the corner. That's Paul Duval's. And this thing over here, which I really want to see put together, is Mario's new Star Party telescope. Made of
Ooh,
graphite and carbon fiber and God knows what all. So stop over and talk to Mario about it before you leave. Both show and tells look really interesting tonight. And we've got a telescope set up outside where Saturn is lurking and maybe some aurora a little dimmer than last night. Off you go. Thank you.
thank you.
Mike.
Have a great time, everyone. Good night.
Bye.
Bye-bye, everybody.
Bye.
It's really true that when you're in the middle of your PhD and things are going, you know, you're about as smart as you'll ever be. Yeah.